There are few moments in science when we sense, viscerally, that we may be on the verge of something extraordinary. Moments when the vast, silent canvas of the cosmos, for a brief instant, seems to speak. And now, just maybe, it has. In a small patch of sky, far from the glare of our own sun, orbiting a dim and ancient red star, there lies a world not like our own. It is heavier, larger, stranger. It is bathed in the ruddy glow of a star that will outlive us all. And yet, this planet, known only by the designation K2-18b, may be whispering to us across the interstellar dark. It may be whispering the signature of life, not a message, not a civilization, not yet, but something more primal. A molecule, a breath, a pattern in the spectrum of starlight that, if confirmed, could represent the first evidence that we are not alone in the universe. To some, it may sound unremarkable. After all, we've long believed that life must exist beyond Earth. The numbers alone are overwhelming, hundreds of billions of stars in our galaxy, each with the potential for planets. Life, we suspect, is not a miracle of Earth, but a probability of nature. But belief is not knowledge. Hope is not evidence. And so, we wait. We build our telescopes. We peer deeper into the cosmic dark, not to satisfy curiosity alone, but to find truth. And now, through the lens of the James Webb Space Telescope, we may have come closer than ever before. It began with water. In 2019, scientists using the aging yet still powerful Hubble Space Telescope observed water vapor in the atmosphere of K2-18b, a world more than twice the radius of Earth, orbiting in the habitable zone of its star, and now possibly hosting water. It was tantalizing, but not conclusive. Water alone is not life. Venus has water vapor in its clouds, and Mars once had rivers. Yet neither teems with the kind of vibrant biosphere we see here on Earth. Still, the signs were promising. Then, in 2023, Webb turned its gaze to the planet. With infrared vision far superior to any observatory before it, it analyzed the starlight that filtered through the planet's atmosphere during transit when K2-18b passed in front of its host star. And what it found sent ripples through the scientific community. Not just water, but methane, carbon dioxide, and perhaps, just perhaps, dimethyl sulfide. Here on Earth, dimethyl sulfide is produced almost exclusively by life. It is the molecule you smell near the sea, a byproduct of phytoplankton, the tiny organisms that form the base of the marine food chain. It is not a chemical easily formed by volcanic processes or photochemistry. If it truly exists on K2-18b, it may represent something profound, a biosignature. A sign that, in the vastness of space, biology has emerged a second time. Let us pause for a moment and consider what that would mean. For centuries, we have speculated about life elsewhere. It has inspired our fiction, our philosophy, even our fears. But never, until now, have we had something like this, tangible, measurable, scientific. If life has begun on K2-18b, then it has begun twice in the universe, once on Earth, and once 124 light-years away. And if it can begin twice, it may be everywhere. That realization alone would transform our understanding of biology. It would tell us that life is not an accident, but a feature of the universe. That the same laws of chemistry and physics that govern the stars and galaxies also give rise to molecules that replicate, evolve, and eventually wonder. But we are not there yet. Science demands caution. The detection of dimethyl sulfide is still tentative. A 3 sigma signal, meaning there's a 0.3% chance it's a statistical fluke. Significant, but not definitive. To claim the discovery of life, we will need more data, more observations, perhaps years of study. And yet, we are close, so close. In this documentary, we will explore the full story of K2-18b, how it was discovered, what we know of its nature, and what makes it such a compelling candidate for extraterrestrial life. We'll dive into the chemistry, the physics, and the astrobiology of this world, and we'll ask a question that has haunted science for decades. This planet, K2-18b, may not give us that answer, but it might offer the first clue. And from there, everything changes. Because if we can detect one, we can detect many. If biology is out there, it will not remain hidden for long. We are no longer just observers of the stars. We are listeners, interpreters, seekers of meaning in molecules. And the next great revelation may not come from within our own minds, but from the light of an alien world. K2-18b, an ocean world hidden in starlight. It is a strange truth of our time that we are now more familiar with the atmospheres of planets light years away than with the depths of our own oceans. But perhaps it is not so strange. The universe beckons in ways that the Earth does not. It reveals its secrets to those with patience and light, and above all, to those who know how to listen. K2-18b is one of those secrets. It is a planet that orbits a star known simply as K2-18, a small red dwarf located 124 light-years from Earth in the constellation Leo. It does not shine brightly in our skies. You could not see it with the naked eye, and yet it has become the focus of intense scrutiny, not because of what it is, but because of what it might hold. Let us consider the fundamentals. K2-18b is what astronomers classify as a sub-Neptune. It is roughly 2.6 times the radius of Earth, and 8.6 times as massive. If we could stand upon it, and we probably couldn't, its surface gravity would be nearly twice that of Earth. A human body would feel heavy, burdened, as though the planet itself were trying to keep you close. But we likely would not stand on it at all, because K2-18b is almost certainly not a rocky planet. It is enveloped in a thick atmosphere, rich in hydrogen and helium. And beneath that atmosphere, if the models are correct, lies a vast global ocean. This class of exoplanet is still theoretical. We call them Hycean worlds, planets with deep oceans of liquid water beneath hydrogen-rich skies. They are unlike anything in our solar system. Not gas giants like Neptune, not rocky worlds like Earth, but something in between, a hybrid of atmosphere and ocean. Heat and chemistry, wrapped around a planetary core we cannot see. For decades, scientists imagined that life elsewhere would require a planet like ours, solid surface, moderate temperatures, thin atmosphere. But our observations have forced us to reconsider. Hycean worlds may be far more common than Earth-like ones, and they may, in many ways, be better suited for life, particularly microbial life that thrives in aquatic environments. On Earth, the first life emerged in water, perhaps in shallow pools heated by volcanic springs, or perhaps in the cold darkness of the ocean floor, near hydrothermal vents. These environments were protected, chemically rich, and persistent. Could the same be true for worlds like K2-18b? Let us examine its star. K2-18 is a red dwarf, the most common type of star in the galaxy, smaller and cooler than our Sun. Red dwarfs burn their hydrogen slowly, with lifespans measured not in billions, but in trillions of years. They are cosmic elders, destined to outlast even the last white dwarfs in the distant future. K2-18b orbits its star every 33 Earth days, placing it squarely within the habitable zone, the region where temperatures may allow for liquid water to exist on a planet's surface, or beneath its clouds. But red dwarfs are a mixed blessing. Because their habitable zones are so close to the star, planets within them often become tidally locked, with one side perpetually facing the star and the other cast in eternal night. They are also vulnerable to stellar flares, bursts of radiation that can strip away atmospheres and sterilize planetary surfaces. Yet there is hope. Recent studies suggest that some red dwarfs, like K2-18, may flare less frequently, and a thick hydrogen atmosphere could protect the oceans below from radiation. If such a world is indeed covered in water, then even a tidally locked configuration might still allow life. Circulation of heat through atmospheric winds or ocean currents could keep the planet temperate and stable. It is difficult to imagine what such a place would look like. If you could descend through the atmosphere of K2-18b, the light would grow dim and red. The sky would not be blue, but a murky, copper hue. Clouds would gather thickly, laden with vapor, refracting starlight into strange patterns. And below, Perhaps an ocean, an endless sea without continents or islands, no shore to stand on, no mountains to climb, just liquid depths and chemical complexity. In that alien sea, shielded from the harshness of space by kilometers of atmosphere and hydrogen gas, life might begin, not as complex animals or thinking minds, but as single-celled organisms, microbes, plankton-like entities that drift, metabolize, reproduce. In other words, the kind of life that gave birth to all others. Of course, we cannot see that ocean directly, not yet. What we have, instead, is spectroscopy, a science of inference. When K2-18b transits its star, a small fraction of starlight passes through its atmosphere before reaching our telescopes. Certain molecules absorb certain wavelengths of light, creating a fingerprint, a set of absorption lines that tell us what gases are present. That is how we know about the water vapor, the methane, the carbon dioxide, and perhaps, most intriguingly, the dimethyl sulfide. None of these molecules alone prove that life exists on K2-18b. They can all be produced by non-biological processes, volcanism, photochemistry, reactions between rock and gas. But together, in the specific ratios observed, they are suggestive. On Earth, this combination is found almost exclusively in marine biospheres, in ecosystems driven by microbial life. It is not a discovery, but it is a possibility, one that grows stronger with every observation and every new piece of data. K2-18b has become, in many ways, our first real candidate for an inhabited world, not a mirror of Earth, but something more ancient, more elemental, a planet of oceans and molecules, chemistry and time, and perhaps, if we are fortunate, a planet where life has taken root in the darkness beneath the clouds. What would that mean? It would mean that life is not the rare consequence of planetary coincidence, but the natural product of planetary chemistry. It would mean that the universe does not just allow for life, it encourages it. And it would mean that we are not alone, not even close. What the molecules are telling us. No song sung beneath the stars, no whispered declarations drifting between the galaxies. And yet, the universe speaks. It speaks through light, through the long, patient journey of photons across millions of years. It speaks in patterns, in the gentle sway of gravity, the symmetry of atoms, the geometry of orbits, and sometimes it speaks in the language of molecules. On a world like K2-18b, we cannot yet see oceans or clouds or distant shores. We cannot send spacecraft to skim its atmosphere or dive beneath its waves. But we can catch a few rays of starlight, filtered through its sky, stretched and shifted by its chemistry. From this light, we read its story. When the James Webb Space Telescope observed K2-18b in 2023, it did so not by imaging its surface, but by observing a transit when the planet passed in front of its host star, blocking a tiny fraction of its light. As this light passed through the planet's atmosphere, certain wavelengths were absorbed by gases, while others were allowed to pass. The result was a spectral fingerprint, a barcode of sorts, etched in infrared. It was this fingerprint that first confirmed what Hubble had already suggested: water vapor in the atmosphere of K2-18b. Not ice, not liquid, but vapor suspended in its upper atmosphere, possibly condensing into clouds. This was important. But it was only the beginning. Alongside the water, JWST detected methane and carbon dioxide, both carbon-bearing molecules, both vital in the story of life on Earth. And then came a surprise. The data contained hints, faint but persistent, of dimethyl sulfide, or DMS. Let us begin with the more familiar molecules, methane and carbon dioxide. Methane, on Earth, is produced in two main ways. It can arise abiotically through geological processes like serpentinization, where water interacts with certain types of rock under high pressure and heat. It can also come from biological activity, from microbes in wetlands, from the digestion of animals, from the decomposition of organic matter. Carbon dioxide is similar. It is a byproduct of combustion, of respiration, of volcanic activity. It is both a lifeline and a danger, essential for warming Earth but catastrophic in excess. The presence of both CH4 and CO2 on K2-18b in itself does not confirm life, but the ratio of these gases is curious. On Earth, their relative abundances are tightly linked to biological cycles. Methane is quickly destroyed in our atmosphere by sunlight and chemical reactions. If it is present in significant quantities, it must be constantly replenished. The same appears to be true on K2-18b, which raises the question, what is maintaining the balance? Is it chemistry? Is it geology? Or is it biology? Now we come to dimethyl sulfide, the molecule that has caused such a stir in the astrobiology community. On Earth, DMS is not just produced by life. It is, as far as we know, produced only by life. More specifically, it is released by marine phytoplankton, microscopic organisms that inhabit the sunlit layers of our oceans. As they die and break down, they release dimethylsulfonopropionate, which is then converted into DMS. It rises into the air, influencing cloud formation and even the planet's climate. It gives the sea its smell. And if the detection on K2-18b is real, and that is a significant if, it would suggest not just chemistry, but biology, a biosphere, a living ocean. But how confident can we be? The detection of DMS was made using JWST's mid-infrared instrument, MIRI. It was independent from the earlier measurements made by its NIRS-SPEC and NIRIS instruments. That's important. It means the signal didn't come from noise in a single channel, or an artifact of a specific instrument. Statistically, the detection sits at 3 sigma. That means there is a 99.7% chance the signal is real, and a 0.3% chance it is a fluke. In physics and astronomy, we typically require a 5 sigma detection, corresponding to a 1 in 3.5 million chance of being wrong, before claiming a discovery. The team behind the DMS claim has requested more time with JWST to confirm their result. If granted, and if the signal holds, it will likely become the strongest biosignature candidate in the history of observational astronomy. Still, caution is warranted. There are non-biological pathways for methane and carbon dioxide. DMS is harder to explain, but not impossible. It could be a byproduct of some exotic photochemistry in hydrogen-rich atmospheres. Perhaps a process we have not yet seen on Earth, or not under the conditions of K2-18b. Astrobiology, by its nature, walks a fine line between evidence and enthusiasm. We want to believe, but belief must wait for confirmation, and so the debate begins. Could this be a new class of chemical system? A prebiotic chemistry producing DMS analogs? Could it be a fluke? A data reduction artifact? A misidentification? To strengthen the case, researchers turn to models. They simulate K2-18b's atmosphere under different assumptions: volcanic outgassing, photochemical equilibrium, hydrothermal vents, and again, the models suggest that abiotic sources struggle to produce the observed concentrations of these gases together, especially DMS. Moreover, the concentrations are high, significantly higher than what we see on Earth. That's surprising, but not necessarily problematic. In fact, some theoretical work had predicted exactly this outcome for Hycean worlds with life. A thick hydrogen atmosphere traps heat and slows chemical reactions. Gases that would quickly dissipate on Earth could linger far longer. And in an ocean world without continents or seasonal turnover, microbial life could dominate the biosphere almost entirely, leading to a planet-scale bloom of organic chemistry. In short, the fingerprint matches. It is not proof, but it is not coincidence either. There is, of course, one more tantalizing possibility. If K2-18b is not an ocean world, but a small gas dwarf with no surface, then the presence of DMS becomes far more difficult to explain by natural processes. There would be no ocean in which microbes could thrive, no seafloor, no hydrothermal vents, just gas. In that case, the detection would no longer be a biosignature. It would be something else entirely. It would be a technosignature, a sign not of biology, but of technology, of intelligent life releasing complex molecules into its atmosphere. There is no reason to believe that is the case, but it cannot be dismissed out of hand. Because once you eliminate the biological and the geological, what remains? And so, we are left here, suspended between hope and hypothesis, between signal and noise. The molecules are whispering. They may be speaking of biology, or chemistry, or something we have never seen before. If K2-18b holds life, it will reveal itself not with trumpets and declarations, but with molecules drifting silently in the light of a red star. All we need to do is continue to watch. Could life thrive there? To ask whether life exists on K2-18b is to ask more than whether molecules can survive there. We are not merely seeking chemistry, we are seeking biology. Not atoms, but cells, not reactions, but replication, and that is a far deeper question. Because life, once begun, is persistent. It adapts, it evolves, but to begin, to truly take hold, it needs more than the right molecules. It needs an environment that can sustain it, protect it, nourish it, let it grow. Could K2-18b be such a place? Let us imagine, not from the stars above, but from the sea below. Beneath its thick hydrogen-rich atmosphere, K2-18b may conceal a vast global ocean, perhaps hundreds of kilometers deep. Unlike Earth's oceans, it would have no continents, no islands, no shallows, no shores on which to crawl and evolve limbs, just water, deep, dark, and endless. At the top, the ocean would be blanketed by an atmosphere rich in vapor, perhaps turbulent with clouds. But as you descend, the light would vanish, filtered by kilometers of water. The pressure would rise to unimaginable levels, and somewhere far below, there might be a rocky core, a silent surface warmed by the slow release of radioactive heat and tidal forces. It is here, in this profound darkness, that life might begin. On Earth, life may have originated in just such a place. Hydrothermal vents, deep beneath our oceans, are cracks in the seafloor where heat and minerals pour into the surrounding water. Around them, entire ecosystems thrive, ecosystems that do not rely on sunlight, but on chemistry, on chemosynthesis, on the conversion of chemical energy into biological order. Tube worms, giant clams, and swarms of microbes form colonies around these vents, bathed not in light, but in sulfur. If K2-18b has such vents, they could be cradles of alien life. Even in the absence of a rocky surface, there may be floating layers of water ice or supercritical fluids that allow for chemical gradients, gradients that drive metabolism, that allow molecules to store and release energy, the fundamental requirement of life. The ingredients may be there. The processes may be there. The question is, can life, once sparked, thrive? Let us consider the challenges. The most obvious is gravity. K2-18b is significantly more massive than Earth, which means its surface gravity could be nearly twice as strong. On land, that would make life difficult. Walking, flying, even circulation of fluids within organisms would be more taxing. But in water, gravity's effects are softened. Buoyancy helps. Organisms float, drift, swim. The ocean becomes a protective womb. Indeed, the earliest life on Earth remained in water for billions of years. Complex, multicellular organisms evolved under the surface long before the first fish ever contemplated the land. So perhaps gravity would not be an obstacle, at least for microbes and other soft-bodied creatures. On Earth, sunlight powers the biosphere. Photosynthesis turns light into sugar. But if K2-18b is a Hycean world, its oceans may be so deep and its clouds so thick that sunlight never penetrates far. Photosynthesis, at least as we know it, may be impossible. But again, Earth shows us a way forward. In the deep sea, life thrives without sunlight. Chemosynthetic organisms use hydrogen sulfide, methane, and other compounds as energy sources. Similar processes could exist on K2-18b, where abundant hydrogen and carbon-based molecules offer potential fuel for alien metabolism. Perhaps, in the darkness beneath its clouds, Entire ecosystems have evolved based not on light, but on chemistry. Still, one must ask, could life evolve intelligence in such a place? This is a more delicate matter. Intelligence, at least in the form we understand it, arises from complexity, from ecological interactions, long-term memory, communication, and environmental pressure. Life in a featureless, endless ocean may lack many of these drivers. Without land, there are no tools, no fire, no metallurgy. Even building a shelter becomes difficult. How does one smelt metal in a deep ocean? How does one harness electricity? In short, even if life thrives, it may remain simple, and that may be the answer to one of the deepest mysteries in all of science, the Fermi Paradox. The paradox asks, if the universe is teeming with habitable planets, perhaps even with life, then where is everyone? Why do we not see evidence of advanced civilizations? No spacecraft, no signals, no ruins on the moon, no great Dyson spheres harvesting starlight. Just silence. Perhaps the answer is this, but intelligence is rare. And not because evolution doesn't favor it, but because most life is born in worlds like K2-18b. Worlds with oceans but no land, with pressure but no fire, with chemistry but no tools. Civilizations may never arrive, not because they fail, but because they never had the chance. The universe may be filled with biospheres, but almost devoid of technospheres, a sobering thought, but also a hopeful one. It means we might find it elsewhere, on Europa, on Enceladus, beneath the ice of exomoons and dwarf planets. It means that we are no longer wondering if we are alone, but how many neighbors we have yet to meet. And perhaps, one day, we will not only observe them, but help them. Imagine a distant future in which humanity becomes the uplifter, the bridge between worlds locked in their oceans and the cosmos that waits beyond. We, born of a planet with both ocean and land, might be the rare creatures who escape, who travel, who share, who listen not just for voices, but for life itself, in whatever form it may take.
In the year 2020, we have images of black holes, breathtaking panoramas of the Milky Way, detailed snapshots of distant galaxies, and the stunning James Webb Telescope is getting ready for launch. However, 30 to 35 years ago, everything was so different that such news would likely have shocked engineers and scientists. If we had the opportunity to call a scientist directly in the year 1985 and ask a couple of interesting questions, like the existence of planets around other stars, they would probably say that it's likely, but not certain. Now, it's not 1985 anymore, and thanks to new methods and modern technology, today we have thousands of stars in our own galaxy that have their own solar systems. We have discovered planets of various sizes, characteristics, and masses at various distances from their stars. We have planets even larger than Jupiter that orbit stars in less than 48 hours, and NASA's Kepler mission has made a huge contribution to the search for such planets. It's no longer breaking news that Earth-like planets are being discovered. But let's reason more simply. As each of us has a specific idea of what intelligent life is, and each of us has an idea of the conditions under which this life can exist. Let's imagine a simple analogy: intelligent life in the universe and an ordinary tree. If I ask you whether a tree can grow inside an iron box, or whether it can exist there, you would accurately say no, because you understand that a tree requires certain ingredients, such as soil, fresh air, sunlight, and some nutrients. In fact, the logic is such that we just need to find the same things that exist on Earth, and then we will surely find life. This is how we think now. But consider the fact that you are not Mickey, defining the concept of life only like the one on our Earth, because you haven't seen any other life, heard nothing about it, and are unlikely to hear about it in the near future, and maybe never. So, if we set ourselves the question of searching or pondering whether intelligent life exists in the universe, it's important to understand correctly what form or type of life we want to find. It could be similar to us or something entirely different. Of course, the simplest ways to answer such a question are to apply mathematics, probability theory, and real observations. But in that case, once again, we will be looking for life solely similar to ours. Remember that tree I mentioned? The key point is that we know what it looks like and what conditions it needs. Therefore, we can easily predict where a tree can grow and where it's extremely impossible. If you want a simple answer to the question of whether life exists somewhere in the universe besides us, I will say that it's 100% likely, given what we consider as life. I know this is my personal opinion, but I will try to explain why I'm confident about it. I present to you 10 amazing places in the universe with a full potential for the formation of life. It's not a secret that soon after the formation of our planet, life appeared on Earth and is progressing today. Of course, it's possible that earthly life didn't originate on Earth, but came from somewhere else through natural cosmic processes. And in this conversation, it doesn't matter whether it originated here or somewhere else. What's important is that the basic ingredients for life exist everywhere we look. For example, consider a dozen places where these ingredients are most frequently found. First, there's gas ejected from young objects, like the Herbig-Haro objects, which contain various organic molecules. Another example is protoplanetary disks, where there's a vast diversity of complex compounds and organic molecules. For instance, there's the protoplanetary disk around the young star, H.L. Tauri, photographed by ALMA. The gap in the disk indicates the presence of new planets, and spectroscopic measurements reveal a large variety of carbon-containing compounds, which are essential for life. Even on Pluto, there's thallium and methane, and a rich organic haze. Even in the images from the New Horizons mission, atmospheric hazes are clearly visible and measured for the content of several carbon-containing compounds. Nebulae illuminated by a bright young star are rich in numerous complex carbon compounds, are reflective nebulae for containing a wide variety of complex organic molecules. Reflective nebulae are common sources of raw materials for life. By the way, inside meteorites, there are numerous amino acids and proteins, some of which are not found in nature on Earth. For example, the Murchison meteorite that fell in Australia in the 20th century. The fact that there are more than 80 unique types of amino acids suggests that basic ingredients for life, or even life itself, could have formed differently somewhere else in the universe, perhaps even on a planet that is not orbiting a sun-like star. The gas in the galactic center includes vital compounds. Idol's Pharma is responsible for the recognizable aroma of raspberries, though Russian scientists don't acknowledge this. For example, the wave image of the galactic center shows us stars and gas, with a tremendous amount of material, including heavy elements and organic compounds, which are essential precursors for life. And this is the molecular cloud of Taurus, where new stars are formed. It contains dozens of organic substances, including carbon chains. For example, in the image, the brighter areas in red have the highest density and active star formation, while the blue areas correspond to cooler, less dense regions. However, organic molecules are found in both places. Planetary nebulae formed by the death of sun-like stars contain more than 20 molecular species, including fullerenes. These are abundant on Earth. Interestingly, fullerenes and complex organic compounds can form rapidly and survive to a significant extent during the evolution of any star. Nitrogen, hydrogen, and oxygen are strongly highlighted in this planetary nebula. Different colors clearly indicate the locations of various elements, which are separated from each other. Complex molecules, including fullerenes containing 60 carbon atoms each, have been detected in these planetary nebulae. And you don't have to go far. Sedimentary rocks on Mars contain rich organic compounds, some of which are over 3 billion years old. For example, the American NASA rover on Mars discovered ancient organic molecules embedded in sedimentary rock deposits that have existed for billions of years. They contain carbon and sulfur and could be associated with life beyond Earth. Over the past decades, our knowledge of the existence of planets around other stars has grown to incredible numbers. The number of known exoplanets has changed from a few dozen to more than 1,000 officially confirmed objects. Therefore, now we are confident that exoplanets can come in various sizes, be at different distances around all types of stars, have different masses and characteristics, and these are real data. It's not surprising that against the backdrop of such acquired knowledge, various questions arise in our minds. seemingly logical at first glance. For instance, when will we find the first inhabited planet beyond the solar system? Or what does habitability on a planet actually mean? Do planets exist that closely resemble our home, Earth? All this is done in order to understand where else life might exist. However, the thing is, the more we learn, the more we realize that being interested in and searching for a planet similar to ours with the presence of life is very inappropriate. This is because the universe is incredibly diverse, and places with the presence of life might not be anything like Earth. Perhaps these conditions could be even better or completely different from what we can imagine. We'll talk about why the assumption that a planet similar to Earth is a requirement for the existence of life is misleading. Having only one successful example, the planet we inhabit, leads to this kind of misconception. If we look at our solar system with all its planets and moons surrounding us, it becomes obvious that Earth is something unique. Only we know why we consider it special. Maybe it's because Earth is the known world where life originated, was sustained, developed, and flourished. It transformed the biosphere and eventually became complex, diverse, intelligent, and technologically advanced. Scientists are looking for conditions that resemble those Earth has experienced and continues to experience. They assume that a potentially habitable planet with life must be similar to Earth. But this is where they make a crucial mistake, because these assumptions imply that the conditions our Earth has faced are the most favorable for the desired outcome of life. However, as we learn more about the universe and the solar system, we have solid grounds to challenge such an assumption. There are 5 key points we need to consider. The first thing that comes to mind is a planet the size of Earth. After all, it seems like the ideal size for life. If we're too large, we might be enveloped in a massive hydrogen or helium envelope, like Neptune or Uranus. And if we're too small, we might struggle to maintain our atmosphere, like Mars or Mercury. Hence, the conclusion is that Earth's size is the way to life, right? Saturn's moon Titan is smaller than Mars, yet it maintains a denser atmosphere than even Earth. Moons like Europa, a large watery moon of Jupiter, might have ideal conditions for subaquatic oceanic life. Isn't it paradoxical and intriguing? These typical examples are right here in our very own solar system, yet they don't remind us that the potential for life exists in many worlds of vastly different sizes. The size of Earth is not a special prerequisite for life to form. The second point worth mentioning is the so-called habitable zone. If we have a planet the size of Earth with an atmosphere, we need to place it in a favorable location around its parent star to have the necessary temperature for life to initiate. This also seems logical. However, the thing is, a planet much farther from its star can have a denser atmosphere, leading to moderate conditions. A planet with a lower albedo or specific cloud cover properties might be closer to its parent star and still have moderate conditions. Hot planets could thrive in their upper atmospheric layers, while cooler planets could harbor life beneath ice. The habitable zone is a 5th-place starting point, and science has progressed to a point where this simplistic definition is no longer useful. The third point is the ability of a sun-like star. The majority of stars in the universe are red dwarfs, low-mass stars that burn slowly and steadily, in contrast to only about 20% of stars that share the fate of the sun, burning for billions of years before becoming red giants and ending as planetary nebulae. Although red dwarfs mostly have a low mass and undergo very slow nuclear reactions, emitting little light, many planets orbiting them are locked by tidal forces. However, this doesn't mean these conditions impede the formation of life. There is a risk of cutting off unnecessary possibilities by limiting ourselves to our primary assumption. While it's more likely that life in red dwarf systems may be challenging, until we truly start conducting a census of the universe's population, measuring the atmospheric properties of all available planets, we cannot make a comprehensive conclusion that life in these systems doesn't exist at all. The fourth point is that life regulates its own biosphere. This is another key question for which we don't have an exhaustive answer. Can a planet, initially uninhabited and considering only physical and chemical processes, transform and remain habitable during the early stages of simple life? We know Earth has many feedback mechanisms, and we also know that significant external changes might result in only minor changes within our biosphere. Does having simple, early forms of life hold the key to the development of stable, long-lasting life on a planet? After all, the conditions for its origin are more realistic and favorable. If this is the case, we cannot significantly understand what makes a planet potentially suitable for life until we gain a more complete understanding of this matter. The fifth point is the significance of heavy elements. The very first generation of stars consisted mostly of hydrogen and helium. In our solar system, about 2% of the total mass of all objects consists of heavier elements such as oxygen, carbon, nitrogen, and other essential life elements. Stars with a sufficient amount of heavy elements cannot form rocky planets, nor the simple molecules necessary for life. However, where do we draw this line? Can a solar system made up of half heavy elements be sufficient for life to form? And what if the percentage is 10, or even just 1? Or perhaps it could be as high as 500% in the opposite direction. Therefore, regardless of a specific threshold, we lack a clear understanding of whether we are a rarity in the universe or a typical outcome of probability theory. These are just some of the open questions that hinder our comprehension of a planet similar to Earth. An intriguing fact is that the universe plays with numbers. Consider our observations, for example, within the Milky Way. There are approximately 10 billion Earth-sized planets orbiting within the habitable zone of stars similar to our Sun in terms of temperature and mass. A significant portion of different systems have a comparable concentration of heavy elements to our solar system, indicating that a vast number of exoplanets could potentially be candidates for Earth-like conditions. However, there are also numerous exoplanets of a different type that do not meet these criteria. Such planets are far more abundant than those we naively describe as being similar to our own. The quest for Earth-like planets may lead us to overlook many planets in the galaxy where life may have already originated and begun to thrive. In order to discover something, a more unbiased approach would be to observe everything within our capability. Of course, it's easy to argue that Earth possesses all the conditions for life, which should at least allow us to consider the possibility that planets with similar conditions could also harbor life. So let's start by acknowledging the imperfections in our search for life on exoplanets. It's this kind of thinking that ensures we will obtain biased results in any search we conduct. But if, before the search even begins, we simply decide that life cannot exist around red dwarfs, that exoplanets or moons of incorrect sizes or at incorrect distances from their stars will never form life, or that stars with insufficient heavy elements cannot support life-bearing planets, we risk not only overlooking numerous cases of life in the universe, but also the overwhelming majority of habitable planets. The thing is, nearly 80% of the stars in the galaxy are low-mass stars, and there may well be more worlds the size of Mars or Liverpool, smaller than Earth, orbiting these stars than Earth-sized worlds. There's probably a multitude of atmospheric conditions that can permit life at various orbital distances. There might even be more exomoons of significant size around gas-rich massive exoplanets than Earth-sized exoplanets. So how tempting it is to assume that if we have one successful example like Earth, we should seek examples that mimic that known success. However, this is an incorrect scientific approach. The correct approach is to seek as many plausible worlds as possible that could include these conditions, not limiting ourselves to only Earth-like conditions. It's entirely possible that most planets with conditions similar to Earth's are actually inhospitable to life. Meanwhile, many planets with conditions different from ours may be even more suitable for life. Until precise studies reveal the answer, presuming that Earth 2.0 has a precise scientific basis is speculative at best. The story of how the universe became what we see today, from the Big Bang to the vast space filled with galaxies, stars, planets, and life, unites us all. From the perspective of inhabitants of planet Earth, 2/3 of cosmic history passed before the appearance of the Sun and Earth. However, life emerged on our world as far back as we can peer into the past through measurements. It may have appeared even 4.4 billion years ago. This makes us wonder, did life arise in the universe earlier than on our planet? How long ago might it have emerged? To be more precise, how soon after the Big Bang could enough heavy elements accumulate to form planets and possibly life? The answer to this question takes us further into the past than we could ever imagine. Graphite deposits have been discovered in zirconium, which is the oldest evidence of carbon-based life on Earth. The amount of carbon-12 found in these deposits dates the emergence of life on Earth to over 4 billion years ago. Of course, we cannot travel back to the very beginning of the universe, because after the Big Bang, there were not only no stars or galaxies, there were not even any atoms. Everything takes time to come into existence, and the universe, after giving birth to matter and antimatter, started from a fairly homogeneous state. The densest regions comprised only a small fraction, possibly as small as 0.3%, denser than the average. This means it would take an enormous amount of time for gravitational collapse to work on creating, for example, planets that are much denser than the average density of the universe. Yet, the universe had enough time for all of this to come into existence. If we look at the standard timeline of the universe's history, Earth appeared only after 9.2 billion years after the Big Bang, but many of the steps necessary for creating a world like ours happened very early on, just after 1 second. Antimatter annihilated with the majority of matter, leaving a small amount of protons, neutrons, and electrons. A sea of neutrinos formed, and after about 3 to 4 minutes, protons and neutrons combined to form neutral atomic nuclei, but most of these were isotopes of hydrogen and helium. Only when the universe cooled down to a certain temperature, which took approximately 380,000 years, did electrons join these nuclei, forming neutral atoms. However, even with these fundamental ingredients, life and rocky planets were still impossible because cooling the universe meant that atomic nuclei formed, followed by neutral atoms. Yet, practically all of these atoms were hydrogen and helium. Only much later did the heavy elements necessary for the formation of rocky planets and life begin to form. But gravitational collapse is a reality. Given enough time, it will change the face of the universe. At first, it progresses very slowly, but it gains momentum as regions of space become denser. The denser the region becomes, the better it is at attracting more and more matter, and the areas that start with the highest density grow faster than others. Our simulations show that the very first stars should have formed approximately 50 to 100 years after the Big Bang. These stars should have consisted solely of hydrogen and helium and could grow to quite large masses, hundreds or even thousands of times the mass of the Sun. When such a massive star forms, it dies within 1 to 2 million years, but in the moment of its death, something remarkable happens, all thanks to its life. All stars synthesize helium from hydrogen in their cores, but the most massive ones not only synthesize carbon from helium, they also progress to oxygen, neon, magnesium, silicon, sulfur, and so on, following the periodic table of elements until they reach iron, nickel, and cobalt. After this, there's nowhere else to go, and the core collapses. This triggers a supernova explosion. These explosions eject a vast amount of heavy elements into the universe, giving rise to new generations of stars and enriching the interstellar space. The increase in the proportion of heavy elements signifies an increase in the number of rocky planets with high density and the quantity of elements necessary for life as we know it. We don't need the average stellar system in the universe to resemble our solar system. We only need a few generations of stars to live and die in the densest regions of space to replicate conditions suitable for the emergence of rocky planets and organic molecules. For instance, in the remnants of a supernova, there exists a slowly rotating neutron star, formerly a massive star that reached the end of its life. Although supernovae can send the synthesized heavy elements back into the universe, it's the subsequent mergers of neutron stars that create most of the heaviest elements. By the time the universe reaches just 1 billion years old, the most distant objects are abundant in heavy elements, as confirmed by our measurements. There is a significant amount of carbon, as much as in our solar system, and other heavy elements accumulate even faster than carbon. It may take more time to achieve a high concentration, because carbon primarily emerges in stars that do not become supernovae themselves. However, carbon is not essential for rocky planets, and other heavy elements also start to accumulate more rapidly. Possibly within several 100 million years after the ignition of the first stars, around 300 to 500 million years after the Big Bang, the most enriched stars have already formed rocky planets. This is seen in the protoplanetary disks around young stars. Gaps in these disks indicate the presence of new planets. As soon as the disk has a sufficient amount of heavy elements, rocky planets can emerge within it. If carbon were not essential for life, similar processes could begin in different regions of the cosmos. However, for life similar to ours, carbon is crucial, which means that the appearance of life may need to wait much longer. Even though carbon atoms will appear in the mix, it will take approximately 1.5 billion years for there to be enough of it. This period is before the universe reaches 10% of its current age. However, it's not just the 5% required for the formation of rocky planets. It's interesting to consider that the universe has formed planets and all necessary ingredients in the right quantities for life to emerge, except for carbon. To create a sufficient amount of this essential ingredient for life, we must wait until the most massive sun-like stars live and die. You see the remnants of supernovae on the left and a planetary nebula on the right. Both of these mechanisms allow stars to return burnt heavy elements to interstellar space, utilizing them for the emergence of stars and planets in the next generation. Sun-like stars, after their death, leave behind planetary nebulae, which are the primary source of carbon in the universe. It takes more time for the production of carbon because stars that give rise to planetary nebulae have longer lifespans than those that perish in supernova. Extrapolating that back into the past, the most advanced forms of life that appeared on Earth in different epochs suggest an interesting exercise. It turns out that the increase in genome complexity follows a certain trend. If we go back to individual paired bases, the time frame suggests something more like 9 to 10 billion years, rather than the 12 to 13 billion years ago the Earth formed. This indicates that life could have emerged a billion years ago. However, in our cosmic region, it took several additional billion years to initiate. On this semi-logarithmic graph, the complexity of organisms, measured by the length of non-redundant DNA relative to the functionally non-redundant DNA, with respect to gene readability through paired nucleotides, linearly increases over time. We do not know this at the current moment. We do not know where the line between life and non-life is drawn. We also do not know if earthly life began here before other formed planets, or somewhere deep in interstellar space without any planets at all. Many amino acids not found in nature have been discovered in the Murchison meteorite, which fell to Earth in Australia in 1969. The fact that over 80 unique types of amino acids exist in a simple cosmic rock suggests that the ingredients for life, or even life itself, might have emerged through interactions on planets. It's intriguing, the elementary ingredients necessary for life appeared shortly after the formation of the first stars, and the most important ingredient is carbon. As the fourth most abundant element in the universe, carbon is the last ingredient to reach the necessary quantity for rocky planets. In some places, rocky planets appeared much earlier than life could have emerged, perhaps as soon as 500 million years after the Big Bang, or even earlier. However, once we have enough carbon, all the necessary steps for the emergence of organic molecules and the initiation of the direction towards life become inevitable. Whatever life processes led to the emergence of humanity, they might have begun when the universe was 10 times smaller than it is now. We can be certain that in our solar system, we are alone. The maximum possibility is the existence of some microbes. These would not be complex multicellular organisms. But where are the intelligent beings? If intelligent beings truly exist in the universe, their location is at least light years away from us. Two independent intelligent civilizations could coexist, excluding interstellar travel. If they followed a similar path as our life, the question arises, where are they? Perhaps we should start with the fact that to emerge, life must go through several stages, yet the ingredients for it are literally everywhere. Even if we limit ourselves to life chemically similar to ours, the universe is teeming with possibilities. Molecules capable of binding, including organic ones, are present both on planets and in space. This is the Omega Nebula, or the Messier 17 mission, an intensely active star-forming region, which explains its dusty and vivid appearance. Stars formed at different stages of cosmic evolution have different proportions of heavy elements. Although Earth formed over 9 billion years after the Big Bang, the universe didn't necessarily have to wait that long. Therefore, we'll categorize stars into 3 population types. The first population type includes sun-like stars, which consist of 1 to 2% heavier elements than hydrogen and helium. They are composed of processed material, and their planetary systems have gas giants and rocky planets suitable for life. The second population type consists of older, ancient stars with only 0.1% of the heavy elements found in the Sun. Most of their worlds are gaseous and rarefied. They are too primitive and contain too few heavy elements for life to emerge. The third population type includes the earliest stars in the universe, which should be almost entirely free of heavy elements. The study of the earliest galaxies indicates that they are mainly composed of stars from the second population type. However, closer to us, there is a mix of young and old stars, rich and poor in metals. In star distances, the scale is accurate in this illustration, but if the picture were to scale, even the largest stars would be smaller than 1/1,000,000th of a pixel. One of the most important lessons for astronomers came from the Kepler mission when examining the Kepler 4444 system. This first population-type star has planets, but they are much older than our Earth. Our planet is only 4.5 billion years old, while the Kepler 444 system is 11.2 billion years old. This means the universe could have formed Earth-like worlds very early, at least 7 billion years before Earth appeared. Considering this possibility and the fact that regions like the center of our galaxy got enriched with metals faster and more significantly than our surroundings, it's quite possible that there are places in the universe, maybe even in our Milky Way, more conducive to the emergence of intelligent life than the Sun-Earth system. Given all that we know about the positioning of stars well suited for the birth of life, such as how closely 2 different civilizations could be, and where we should search for them, the answer might change based on these conditions. Let's consider 5 main possibilities. This is the imagination of an artist regarding the TRAPPIST system, with its planets reflecting light from their surfaces. The potential presence of water on each of these worlds is depicted through seas, ponds, and vapor. However, it's unknown if any of these worlds have an atmosphere or if their parent star blew it away. One thing is clear. Potentially habitable worlds are located close to each other at a distance of only 1 million kilometers. In the early days of the solar system, it's likely that Venus, Earth, and Mars, and perhaps even Theia, a hypothetical planet that collided with Earth, had conditions equally suitable for life. Their atmospheres were filled with life-building ingredients, and there was liquid water on their surfaces. Venus and Mars at distances close to Earth's mark, a trajectory that spanned tens of millions of kilometers. However, around a Class M star, a red dwarf, planets could be separated by distances much smaller, as seen in systems like TRAPPIST-1. Potential habitable worlds could be as close as 1 million kilometers apart. Twin moons or planets orbiting a giant world, or a binary planet, could be even closer to each other. If life successfully emerged under certain conditions, why not have it arise twice, almost in the same place? This is a globular cluster, Omega Centauri apertured using a powerful telescope. Closer to the cluster center, you can see higher density, but the stability is comparable to any other region. Globular clusters are massive collections of hundreds of thousands of stars, forming a spherical shape with a diameter of a few tens of light years. In the outer edges, the typical star-to-star distance is about a light year, but in the denser inner regions of these star clusters, stars can be as close as the Sun and the Kuiper Belt. Orbits in these star systems must remain stable, even in such crowded surroundings. Considering what we know about globular clusters, which appeared much earlier than the Kepler 4444 system, there should be promising candidates for life and habitability within a few hundred astronomical units. Although this distance changes over time due to star motion, you could call this an incredibly close encounter of two civilizations. This high-resolution image operates very close to the infrared range. Such pictures allowed us to discover 3 superstar clusters in the galactic center. Since long-wave light near infrared penetrates the dense dust between Earth and the galactic center, we could observe these superstar clusters. This cluster is from the central parsec, and all stars in these clusters, as well as the galactic center, are quite young. The closer you get to the galactic center, the denser the stars are. In a few light years from the center, star density is extremely high, much greater than the center of a globular cluster. In a sense, the galactic center is an even denser environment with massive black holes and extremely massive stars and clusters forming. While globular clusters lack these, there is a problem with those stars in the sense that we see them in the Milky Way's core. They are relatively young, possibly due to high variability in their local environment. Stars rarely survive there for even 1 billion years, despite the high density. In this area, stars come in different sizes, colors, and masses, including many bright blue stars, which are dozens or even hundreds of times more massive than the Sun. This is evident in the scattered star cluster NGC 3766. So, let's consider the existence of a civilization in a densely packed star cluster, or a spiral arm. Spiral arms are rich in unusual regions of the galaxy, where young stars are more likely to form from these epochs. Star clusters often contain thousands of stars within a region just a few light-years in size. However, stars don't remain in such a configuration for very long. A typical open star cluster disperses in just a few million years, and only a small fraction of them survive for billions of years. Stars constantly enter and exit spiral arms, including our Sun. In summary, while the typical distances between stars within a cluster may be around 1 light-year, they are unlikely candidates as the cradle of life. This logarithmic diagram displays distances, showing the Voyager spacecraft, our solar system, and the nearest star. So, let's consider the latest idea that everything is distributed in interstellar space. In other cases, stars end up in the same situation we observe, distances between them being on the order of a few light-years. Approaching the center of the galaxy, we can reduce this distance to what is encountered in open clusters, approximately 1 light-year. But if we get too close, we face the problems we see in the galactic center: mergers, interactions, and other catastrophic events that are more likely to interfere. To maintain a stable environment, we can reduce the distance, but the typical interstellar space is not suitable for this. If we adjust for close encounters, the best approach would be to wait until another star passes close to the initial one. With a typical star, this happens approximately once every 1,000,000 years. This graph represents the probability of a star passing at a specific distance from the Sun, with both axes being logarithmic. While we don't expect intelligent extraterrestrial life to be a frequent phenomenon in the universe, as common as planets and stars, every world that meets the necessary conditions represents a chance. Each time you get a chance, you gain an opportunity for success, with a finite probability. Each of these possibilities may turn out to be reality, but until we venture there and see what is there and what isn't, it is essential to objectively assess what kind of extraterrestrial intelligence the universe may provide us. The truth is somewhere out there, but it's important to understand that if we were extremely lucky, it could be much closer than we dare to imagine today. The journey beyond our solar system begins through the asteroid belt, a captivating but challenging region filled with countless celestial rocks. Yet, navigating through it isn't as tricky as it sounds. Each asteroid is spread out by vast distances, over 5 million kilometers apart. Spacecraft like Pioneer 1, Pioneer 2, and the Voyager probes have successfully traversed this region without incident. One might even linger here to explore, perhaps pausing near asteroid 243 Ida to glimpse its tiny moon, or observing the enigmatic fog that drifts over the vacant crater of the dwarf planet Ceres. This region also offers rare cosmic spectacles. For instance, the Galileo probe once captured a dramatic collision between comet Shoemaker-Levy 9 and Jupiter. Hidden within the asteroid belt is an intriguing mystery: the hypothetical planet Phaeton. Did this elusive world ever exist? And if so, what led to its fate? For centuries, scientists have debated this. Embark with us on a journey through the belt to search for remnants of this lost planet. What might the DNA of these asteroids, their chemical makeup, reveal? Could Phaeton have been destroyed by a second sun, or does it somehow endure as a ghostly zombie planet concealed in the desolate stretches of our solar system? The story of this mystery dates back to the 16th century, when astronomer Johannes Kepler noticed an unusual gap between Mars and Jupiter. He speculated there might be a planet there, but never pursued it further. In the 18th century, astronomers Titius and Bode revisited the idea, discovering a mathematical sequence that described the distances of planets from the Sun in geometric progression. However, a gap remained within this sequence between Mars and Jupiter, roughly 2.8 astronomical units from the Sun, which aligned with their calculations. Let's explore their findings. The approximate relative orbital distances from Mercury to Saturn are 4, 7, 10, 16, 52, and 100. When subtracting 4 from each, we get 0, 3, 6, 12, 48, and 96. Each result is roughly double the previous value, but there's a gap between 12 and 48, prompting the question, could a planet have once occupied this missing spot, about position 24, situated between Mars and Jupiter? This theory gained further support in 1781 with the discovery of Uranus, which fit precisely within the Titius-Bode sequence. A team of 24 astronomers, known as the Celestial Police Squad, began a dedicated search for the mysterious missing planet. In 1801, Italian astronomer Giuseppe Piazzi discovered Ceres orbiting exactly where this hypothetical planet was expected. Although Ceres turned out to be quite small and was eventually classified as a dwarf planet, many believed it filled the gap between Mars and Jupiter. This idea, however, was short-lived. In 1802, Heinrich Olbers discovered another body, the asteroid Pallas, sharing nearly the same orbit as Ceres. Olbers speculated that Ceres and Pallas were fragments of a once-existing planet. According to celestial mechanics, these fragments would regularly pass through the point of the planet's supposed disintegration. After running calculations, Olbers predicted locations where other fragments might be found. In 1804, the large asteroid Juno was discovered in one of these predicted areas, and in 1807, Olbers himself found Vesta. Over time, astronomers identified an entire asteroid belt in this exact region, reinforcing Olbers' theory and leading the lost planet to be named Phaeton, after the hero in Greek mythology. In the myth, Phaeton persuaded his father to let him steer the sun's chariot, only to lose control, causing devastation as he drew dangerously close to Earth. Zeus stopped the impending disaster by striking Phaeton down, flooding the world to extinguish the flames. In 1927, German historian Franz Kugler studied ancient texts and proposed that the myth might be rooted in an actual celestial event. He suggested that around 1500 BCE, an intensely bright object appeared in the sky, followed by a meteor shower that caused fires and floods across regions in Africa and Asia. While no scientific evidence supports a real event linked to this myth, researchers still debate the possibility that Phaeton's destruction was tied to significant geological changes on Earth. Some even hypothesize that a fragment of Phaeton could have triggered the dinosaurs' extinction. Proposed timelines for the planet's demise range widely, from 3.5 billion years to as recently as 12 to 25,000 years ago. There's less debate over what Phaeton may have looked like. Early 20th century estimates suggested it was a small celestial body, perhaps between the size of Mars and the Moon, with a diameter between 3,500 and 6,800 kilometers. Scientists theorize it orbited the Sun at 2.8 astronomical units, composed primarily of metals, carbon, and silicates, with some asteroids hinting at water on the surface, suggesting that Phaeton likely had water as well. It probably lacked a significant atmosphere, as no remnants have been found. Despite this, scientists have speculated that Phaeton could have supported some form of life in its subsurface layers. By 1992, the hypothetical planet was even classified within our Sun's habitable zone, suggesting conditions that might have allowed simple life forms to thrive. with potentially moderate temperatures and liquid water, despite its smaller size and farther orbit from the Sun. A major scientific breakthrough came with the discovery of frozen complex substances within the main asteroid belt. The Hubble Space Telescope identified traces of water ice and complex carbon compounds on Ceres and Vesta and on asteroid Themis, which was independently confirmed by 2 international teams. This discovery suggests that after Phaeton's destruction, essential building blocks for life may have arrived on Earth through its remnants. Sci-fi enthusiasts and mythology lovers took these findings further, imagining that the hypothetical planet once housed an intelligent civilization that relocated to Earth after its demise. Legends of Atlantis are often woven into these tales, suggesting that Phaeton's inhabitants brought advanced knowledge, possibly explaining historical feats like Egypt's pyramids. Although captivating, such theories remain speculative, with no scientific foundation. Several scientifically supported theories propose different explanations for Phaeton's fate. 7 main hypotheses offer varied scenarios of cosmic catastrophe, each with its own strengths and weaknesses. Many people are quick to place blame on others for their hardships, and similarly, scientists have speculated that Phaeton's destruction might be due to the influences of Jupiter and Mars. These massive planets appeared to play a cosmic game of billiards, with Phaeton as the cue ball. Jupiter's powerful gravitational force tugged Phaeton off course, while Mars's gravity pulled in the opposite direction, tearing Phaeton apart in a chaotic celestial game. 16 million years ago, the planet fractured into countless comets and asteroids. However, astronomers from the Edinburgh Observatory disagree, as their calculations suggest such gravitational interactions would have thrown Jupiter's moons into disarray, requiring over 2 billion years to stabilize. Astrophysicists have observed no evidence of this disturbance. Another theory casts Phaeton as an active participant in this cosmic billiards match. NASA scientists, through simulations, suggest that Phaeton's destruction coincided with a period of heavy bombardment marked by frequent impacts on the Moon, Earth, and Mars. This theory proposes that Phaeton's orbit became unstable due to gravitational pushes from Jupiter and Mars, causing it to stir up the main asteroid belt and set off collisions with other celestial bodies. Over time, Phaeton's orbit stretched dangerously close to the Sun, where it eventually burned up under its intense heat. A more dramatic theory involves another star as the culprit. Some believe there was once a second star in our sky, which eventually exploded in a supernova. This explosion may have engulfed Phaeton and left behind remnants that later formed the asteroid belt. According to this idea, Jupiter was initially this second star, which transitioned into a gas giant after the supernova. Ancient myths from various cultures, like the lost texts from the Alexandrian Library, South African tribal lore, and Mayan chronicles, all mention 2 stars in the sky, with one eventually fading after a massive explosion. One catastrophic scenario involves Mars and Phaeton in a near-fatal approach. The 2 planets drew too close and collided, with Phaeton, the smaller of the 2, shattering from the impact. Mars may have lost its atmosphere and any potential life it might have harbored. However, this theory falls short of explaining why no apparent evidence of such a destructive collision exists on Mars. Another hypothesis suggests that Phaeton's own rotation may have caused its destruction. If the planet spun too quickly, centrifugal forces could have exceeded its structural limits, tearing it apart. Irish astrophysicist Ernst Öpik, however, contests this theory, asserting that such an event would only produce fragments no larger than 25 meters across, or possibly vaporize Phaeton altogether. He suggests that if a rocky planet of this size had exploded, Earth would have experienced deadly radiation and scorching gases that could have annihilated all life. Alternatively, Phaeton may have collided with a satellite or rogue object. In this scenario, Ceres, Pallas, Juno, and Vesta could have been its moons. Phaeton might have had another large satellite near Jupiter that eventually broke free under Jupiter's gravitational influence. This wandering satellite may have orbited independently for millions of years, periodically returning to collide with Phaeton. Eventually, it struck with such force that Phaeton shattered, while the satellite was ejected from the solar system. Another version of this theory involves a rogue planet or a stellar core that strayed into the solar system, altering the orbits of nearby objects before colliding with Phaeton. This impact may have stripped Phaeton's crust, transforming it into scattered asteroids, with the debris eventually reaching Mars, possibly contributing to its loss of water, atmosphere, and any primitive forms of life. Lastly, Phaeton may have been undone by an unforeseen adversary within itself early in its history. Imagine witnessing this on a cosmic journey. Initially, a serene sky with no apparent threat from any planet or asteroid, yet suddenly, an immense explosion would rip through Phaeton, cloaking it in a nuclear cloud. Its remains would scatter into space, eventually forming the asteroid belt. While this scenario seems unlikely, what could trigger such an explosive reaction inside a planet? Natural forces could provide an answer. Earth offers a clue. Natural nuclear reactors can spontaneously occur, as evidenced by the Oklo uranium deposit in Gabon, where a self-sustaining reaction began around 2 billion years ago, fueled by uranium-235, and continued for hundreds of thousands of years before ceasing. On other planets with higher uranium-235 concentrations, similar natural reactors might reach critical mass, potentially triggering a spontaneous nuclear explosion. Though each theory of Phaeton's demise differs, they share one outcome. Remnants of the planet should remain where it was destroyed. Indeed, we find these in the asteroid belt. But that's not all. Phaeton's core might still exist. Some scientists propose that its core may be nearby, playing a key role in our lives. It could be the moon. Stripped of its crust and much of its mass, this object may have drifted close to Earth, becoming captured by its gravity. Myths from the Maya and African tribes even speak of a fireball appearing in the sky around 12,000 years ago, from which the moon was born. Is Phaeton ruled out? Despite the allure of ancient myths and compelling theories, recent research seems to steer us in another direction. The idea of Phaeton persisted for nearly 2 centuries until the late 20th century, when a fundamental issue emerged. The sheer energy required to destroy an entire planet was staggering, and its source remained unknown. While proponents of the theory sought a solution, by the late 1990s, new studies and refined models of the solar system revealed that the total mass of the asteroid belt is just about 0.05% of Earth's mass, far too little for a planet. Even combined, these asteroids wouldn't form something as large as the Moon. They amount to only 4% of its mass, barely the size of Charon, a small moon of Uranus with a diameter of about 1,200 kilometers. Additionally, recent calculations show that Jupiter's gravity would have prevented a full-fledged planet from forming in the asteroid belt. Most importantly, studies found that the celestial bodies in this region have diverse chemical compositions, suggesting they aren't fragments of a single body. So how do we account for the vast cluster of rocks between Jupiter and Mars? The prevailing theory is that they emerged through the gradual buildup of material from the solar system's protoplanetary disk. This process, known as accretion, involves bodies accumulating mass by gravitationally attracting nearby matter. To understand accretion, let's journey back about 4.6 billion years, when the solar system was in its infancy, consisting only of the Sun and a massive cloud of gas and dust, the protoplanetary disk from which planets would eventually form. In this disk, denser areas gathered more matter through gravity. As these areas grew, they became planetesimals, small building blocks of planets, spanning a few meters to hundreds of kilometers. Some grew large enough to become protoplanets, amassing mass through collisions until they evolved into full-fledged planets. However, not all protoplanets succeeded. Trapped in an unfavorable location between Mars and Jupiter, these developing planets faced the gravitational might of the gas giant. Jupiter pulled some of these protoplanets into its orbit as moons, while others were flung out of the solar system. For most, Jupiter's overwhelming gravity made planetary development impossible, like trying to build a sandcastle in a hurricane's path. Jupiter's disruptive role in the asteroid belt. Jupiter's gravity disrupted the orbits of surrounding celestial bodies, making them unstable and eccentric, which led to intersecting paths and increased the chances of collisions that ultimately shattered them. This influence also accelerated the planetesimals, adding energy and speed, which hindered their ability to accumulate into larger bodies. Thus, the asteroid belt became a kind of graveyard for these thwarted planetesimals, though it remains a dynamic zone filled with asteroids. However, there might be a different twist to this tale. When the asteroid belt initially formed under Jupiter's gravitational influence, the gas giant was closer to the Sun. As it migrated outward, pulling Saturn along, their movement stirred up the solar system, similar to a blender, creating a diverse array of asteroid types, carbonaceous, silicate, and metal-rich. This journey of the asteroid belt remains complex and full of mystery, with much still to be discovered. One intriguing theory suggests that, rather than Phaeton, another planet called Planet 5 might have once resided within the asteroid belt. This concept gained traction after the Apollo missions brought lunar rocks back to Earth, which showed evidence of high-energy impacts from asteroid collisions that were powerful enough to melt them. Radiometric dating revealed that these rocks had cooled around 3.8 to 4 billion years ago, aligning with the late heavy bombardment, a period marked by numerous impacts from comets and asteroids on the Moon. Although cosmic impacts were frequent in the solar system's youth, they suddenly halted and then inexplicably resumed. This strange cycle led scientists to theorize that Planet Phi's journey could explain this pattern. Though no trace of Planet Phi has been found, astronomers imagine it as a bold and influential presence. Likely orbiting between Mars and the main asteroid belt, Planet Phi would have coexisted peacefully until the combined gravitational forces of Mercury, Venus, and Earth nudged it closer to the asteroid belt. There, Planet Phi would have faced orbit-crossing asteroids that bombarded it continuously. Unfazed, Planet Phi may have redirected some comets and asteroids toward the Moon and the inner planets. However, as impacts overwhelmed it, Planet Phi was eventually ejected toward the Sun, where it met a fiery end. Unlike previous theories, this hypothesis doesn't link the asteroid belt's formation to Planet Phi, yet some scientists question the late heavy bombardment theory itself, suggesting that the gas giant's shifting orbits alone could have redirected asteroids. Despite some skepticism, the Planet Phi hypothesis remains a topic of interest. The possibility of other hypothetical planets could further illuminate gaps in our understanding of solar system formation. One such theory posits a fifth gas giant near the Sun long ago. Recent simulations by American researchers indicate that Jupiter likely started farther from the Sun than we observe today. For it to migrate closer, it may have expelled smaller bodies from the system, potentially causing catastrophic disruptions like a collision between Earth and Mars or Venus. If Jupiter had made a sudden jump rather than a gradual shift, it might have even thrown Uranus or Neptune out of orbit. While we don't see evidence of these events, the theory that Jupiter moved inward remains a tantalizing possibility. The fifth gas giant and its journey into the cosmos. If, at the dawn of the solar system, there were not 4 but 5 gas giants, much about our system's formation begins to make sense. During Jupiter's migration, this fifth planet may have been pushed to a remote orbit, or even cast out of the solar system altogether. Evidence supporting this idea includes the recent discovery by Japanese and US astronomers of 10 rogue planets drifting in space without a host star. These findings suggest that planetary ejection from star systems is a common event in the cosmos. Many scientists believe the Milky Way holds countless rogue planets, though they're invisible to the naked eye due to their darkness. These 10 gas giants were detected through gravitational microlensing, a phenomenon where a planet passing between a distant star and an observer bends the star's light, briefly magnifying it. Though astronomers wondered if these planets could have formed independently, much like stars from primordial gas clouds, they concluded that gas giants would not likely form this way. If they did, the number detected in each survey would be far fewer. This points to the likelihood that these planets once resided in star systems, but were expelled by the gravitational forces of large neighbors or nearby stars. If this theory holds, the galaxy may host as many wandering planets as it does those orbiting stars, perhaps even including our own elusive fifth gas giant. Theia, another hypothetical planet, didn't drift alone through the cold void, but met a fiery end, leaving behind an irreplaceable legacy for Earth, our moon. The moon's origins remain a mystery, yet one leading theory suggests it was born from a colossal collision between Earth and a Mars-sized protoplanet named Theia. This impact likely occurred during Earth's early formation, when it had achieved about 90% of its current mass. Instead of a direct hit, the collision was glancing, unleashing an energy estimated at 100 million times more than the impact that ended the dinosaurs. The force of this impact caused Earth to spin faster, completing a rotation every 5 hours, with a notable axial tilt. Fragments of Theia and parts of Earth's mantle were ejected into space, eventually coalescing under Earth's gravity to form the Moon. This theory aligns with many aspects of the Moon's structure and the Earth-Moon relationship. Initially, scientists doubted that such a precise glancing blow was possible, but later simulations confirmed it as feasible. Recent research from an American geophysics team suggests Theia formed in the same protoplanetary disk as Earth, not as a rogue object. As they grew, their paths inevitably crossed, leading to Theia's catastrophic collision with Earth. While Earth, being larger and more resilient, survived, Theia shattered, leaving fiery debris that initially formed rings around Earth, similar to Saturn's, which eventually coalesced into the Moon. Tyche, the hypothetical ninth planet. Far beyond the Oort cloud, on the distant edges of the solar system, another potential planet, Tyche, might be influencing the cosmos. Researchers at the University of Louisiana have calculated that a massive planet could exist in this remote region, acting as a cosmic snowball launcher. For years, astronomers speculated that the Sun might have a distant companion, possibly a faint star like a red or brown dwarf, dubbed Nemesis. However, observations have yet to reveal its nature, as it hasn't been spotted directly. The last time this mysterious body passed close to the Sun was around 30 million years ago. Further research suggests this companion might actually be a planet rather than a star, with the name Tyche. Calculations estimate Tyche is at least 1.4 times the size of Jupiter. Its gravitational influence could be responsible for sending approximately 20% of all icy comets towards the inner solar system, with some reaching sizes of up to 2 kilometers in diameter. If Tyche were to hurl one of these massive icy bodies toward Earth, the results could be catastrophic, as a comet of such size could theoretically wipe out life on the planet. Distinct from Tyche, another hypothetical resident of the outer solar system, Planet X is believed to be tranquil, posing no threat to Earth. Estimated to be about 10 times the mass of Earth, Planet X is captivating, with a potential orbit around the Sun lasting 10,000 to 20,000 Earth years. Despite its allure, astronomers haven't directly observed Planet X. Its existence is inferred through mathematical models. Scientists have noticed disturbances in the orbits of distant celestial bodies, suggesting gravitational influence from an unknown object. Some astrophysicists speculate it could be a small black hole, while others attribute the anomaly to Planet X's gravity. Interestingly, Planet X might not be alone. Harvard researchers have proposed that another planet, Nibiru, could also be lurking nearby. Adding to this cosmic mystery, an international astrophysics team has speculated that Phaeton, a planet once thought destroyed in a collision with Jupiter, Mars, or another celestial body, could also be out there. This theory emerged after data from the Pioneer and Voyager missions revealed anomalies in the outer solar system, where the probes deviated from their expected paths due to the gravitational pull of an unidentified object, possibly the core of Phaeton, which may have survived its past collision and been expelled beyond Pluto. Imagine if a new planet joined our solar system. Would it harmonize with the existing planets, perhaps even bringing benefits, or would it trigger cosmic chaos? University of California scientists recently modeled such a scenario. In their simulations, they introduced a super-Earth, a rocky planet larger than Earth but smaller than the gas giants, between Mars and Jupiter. Their choice was inspired by recent discoveries from NASA's Kepler and TESS missions, which revealed that super-Earths are among the most common planet types in the Milky Way, though curiously absent in our solar system. The asteroid belt's location between Mars and Jupiter, spanning 550 million kilometers, could theoretically host a super-Earth. Running 1,000 simulations, researchers experimented with super-Earths of different masses and distances between Mars and Jupiter to predict their effects on the solar system. Starting with a super-Earth twice the size of Earth, they positioned it at 2 or 4 astronomical units from the Sun. Inner planets like Mercury, Venus, Mars, and Earth were most vulnerable. Many simulations showed these planets being ejected from the solar system. The outer planets fared slightly better, with Jupiter and Saturn remaining stable, though Uranus risked disruption due to the chaotic influence on its moons. A more extreme model introduced a super-Earth similar to TOI 2095c, over 7 times the mass of Earth in the asteroid belt. This scenario led to severe disturbances. Jupiter and Saturn's orbits elongated, ejecting the new planet, and eventually, Uranus, into space. The inner planets were also affected, with Mars projected to be ejected within a few million years, followed by Earth in some cases, whose orbit would deviate drastically, rendering it potentially uninhabitable. Astronomers liken the solar system to a finely tuned clock, where even small changes can disrupt the delicate balance. Thus, adding a new planet could destabilize the entire system. The absence of a planet between Mars and Jupiter, or at the solar system's edge, likely preserved this gravitational harmony, ultimately protecting Earth and sustaining life. But there may yet be hope for Phaeton, the goal of our cosmic journey. If a planet did form within the asteroid belt, it could remain safe, provided it stayed precisely within 3 astronomical units from the Sun and remained no larger than Mars. Like the ancient Greek legend of steering a careful path, this scenario, though speculative, reminds us of the delicate equilibrium that holds our solar system together. The planets we have studied thus far reside firmly within the domain of scientific theory. Yet, it is essential to acknowledge that new celestial bodies could emerge in our solar system at any moment. Among these potential newcomers are rogue planets, as previously discussed. But why have we not encountered any recent sightings? Notably, there have been no recorded observations of such phenomena in recent years. However, during the 17th to 19th centuries, astronomers documented intriguing accounts of enigmatic planets that appeared and subsequently vanished. For example, numerous sightings reported a celestial object orbiting within Mercury's path, located near the Sun, and it was even captured in photographs. This transient visitor was hypothesized to be a dwarf planet and was designated as Vulcan, only to vanish without a trace shortly thereafter. In 1846, a multitude of astronomers claimed to observe a second moon near Earth, which they named Kleinchen, meaning tiny in German. Like Vulcan, this celestial body also disappeared from view. Many astronomers theorize that these fleeting visitors may have been rogue planets drawn into our solar system by the Sun's gravitational pull. Thus far, these encounters have posed no threat to us. On the contrary, scientists remain eager for the arrival of such a visitor, as it might carry remnants of lost civilizations, offering invaluable material for unique studies and opening up exciting new avenues for cosmic exploration.